Right. All right. We are rolling. Please stand. And by the way, if you need to go to the bathroom or something,
Hi.
please make sure you don't tip over the stand. In nomine Patris et Filii et Spiritus Sancti. Amen. Credo in Deum, Patrem omnipotentem, Creatorem caeli et terrae, et in Iesum Christum, Filium eius unicum, Dominum nostrum, qui conceptus est de Spiritus Sancto, natus ex Maria Virgine, passus sub Pontio Pilato, crucifixus, mortuus et sepultus, descendit ad infernos, tertia die resurrexit a mortuis, ascendit ad caelos, sedet ad dexteram Dei Patris omnipotentis, inde venturus est, judicare vivos et mortuos. Credo in Spiritus Sanctum, sanctam Ecclesiam Catholicam, sanctorum communionem, remissionem peccatorum, carnis resurrectionem, vitam aeternam. Amen. In nomine Patris et Filii et Spiritus Sancti. Amen. It's going to be a little intense on notes, but yes.
Hi, Julia.
Hi, Julia. Everybody is praying for you, and we're trying our best to do a video. If we cut it at 45 minutes, I should just barely have enough space on the iPhone to do this. So, take out your notes, please.
So shouldn't we like be saving the time instead of starting it a minute and a half ago?
What? Oh, we'll be fine. As long as I do it by the end of the hour, we're good. So, it's 45 minutes anyway. So, let's try this. Y equals big fraction.
Mr. Kaufman, can I just zoom it in a little? I think it'll be easier for her to see.
Let me look. Just a second. Oh, they can zoom in. It's high res. That's why it takes up so much space on that thingy. I think it's 720 dpi. Thank you. Yeah. It's really 720 dots per inch, so it's really high res. So on the home computer, they could zoom in on their own and they could see the detail. So this thingy, I would like you to be able to sketch a graph of this thing. Now yesterday we learned a trick called plus minus notation. I'm going to tell you a little bit more about that today. We're going to review it today. Again, plus minus notation is basically a compressed graph. On a number line. And plus minus notation uses what we call 4 different types of breakpoints. Breakpoints are basically any values of x. Whoops, wrong direction. Any values of x. Oops. Where something interesting happens. Oops. Interesting happens. There are 4 types. Can anybody name them for me?
Name what?
The 4 types of breakpoints. Yeah, give me one.
One was vertical asymptotes.
Vertical asymptotes. I'm going to abbreviate mercilessly here. V period ASY apostrophe S is vertical asymptotes. Johnny, give me another one.
Poles.
Poles. We're going to tell you more about those today. Next one? Yeah. Roots. And then the ones we're not really going to use this chapter but still exist.
Definition break.
Definition breaks. Vertical asymptotes holes and definition breaks are what we call discontinuities. It's really a word we don't start using until calculus. Discontinuity means something that interrupts the graph, what makes it not continuous. So if you run into a vertical asymptote, that's definitely discontinuous because it blows up. If you run into a hole, that's a temporary interruption. And a definition break is usually a pretty sudden interruption, like the graph snaps or the graph just ceases to exist, like on the square root of x or radical x. Okay? Now, how do you use plus minus notation? First of all, can somebody name me the breakpoints? Now, whenever you have a function that has a top and a bottom, numerator and denominator, there are certain things you can find on top and certain other things you can find on the bottom. The top gives you what? Which of these 4 breakpoints live on the top? Yeah. Roots. The roots come from the top, from the numerator. What do you find in the denominator? Mainly. Michael.
The denominator.
Roots are on top. What would the denominator give you? I'll give you a hint.
Holes or asymptotes.
Ah, definitely vertical asymptotes are from the denominator. And that's a good question. When do holes show up? Holes show up if you have it in both numerator and denominator at the same time, where they cancel out. So take a look. Do you see any roots? Yeah, okay.
I just have a question.
Go ahead.
So the roots are always going to be on the numerator?
Correct. It will always be on the top. Correct. Speaking of which, this parentheses, what root would that give you? This particular, what location? Go ahead, Sophie, take this one.
What does it mean?
X equals what?
-2?
Good. X equals -2. Is that a single root, double root, triple root?
Double?
Double. What made it do double?
The square?
The squared. There are 2x plus 2's in a row. Julie Miller, give me the next one. Another root.
X equals 3?
Yes.
Okay.
Single, double, or triple?
A single?
Single, because there's only one of them there. And the times 1 is optional. And Jack Lau. Next root.
X equals 4.
4. Single, double, triple, quadruple?
Triple.
Triple root. Good. Depending if it's single, double, or triple, remember that does change the graph. It'll either go straight through, or bounce, or swerve, or something like that. Can somebody tell me any vertical asymptotes?
-1?
Yeah, there's a -1, so x equals -1, single, double, or triple?
Single.
Single. And what else, John? Give me another vertical asymptote.
X equals -5.
Yeah, x equals -5, and that should be a single. Are there any holes? They would say a hole shows up when you have the exact same parentheses on top and on bottom. In this case, no. If there were, we'll show you, we'll do it in the next example. But right now, we have 5 breakpoints, 3 roots and 2 vertical asymptotes, and that's it. There are no definition breaks in this, and there will not be on the test. The only time I'd ever do a definition break is maybe for extra credit. Yeah.
What's a vertical asymptote?
Oh, good question. Yeah, that's right, you weren't here. What is a vertical asymptote? An asymptote is an imaginary line which the graph approaches closer and closer.
Do you just have all this memorized?
Well, this one, yeah. But never touches.
Because that's like
I sometimes change a word or two. I'm not sure what to do. An asymptote is an imaginary line which the graph approaches close and close, but never touches. For example, let's just say take a look here. Here's an example of a vertical asymptote at x equals 3, gentlemen. Okay. Here, you notice the graph is getting closer and closer and closer to it, but it never touches. It'll go infinitely far out. It kind of swerved out of the way because this thing is deadly. This is a division by 0, and the graph is going to die if it hits it. So it's swerving out of the way. It's getting closer and closer and closer, which is perfectly safe as long as it doesn't touch. And that's what happens. Like here, it's like 1 inch away, then a ½ inch, then a ⁄4 inch, then an 1/8 of an inch, then 1/16 of an inch. And it gets teenier and teenier and teenier. You go down 20,000 spaces, the space between the graph and the asymptote is going to be microscopic, but there'll still be a space. Does that make sense? That's a vertical asymptote. That's an asymptote. Vertical asymptote is one that goes up and down. When do they show up? Asymptotes show up usually. They're usually caused. There are very few exceptions by trying to divide by 0. In other words, here's the division. If somebody tries to plug a -1 in here, boom, there'll be a vertical asymptote at -1. If somebody tries to plug in a -5, boom, there's a vertical asymptote at -5. That will cause the graph to swerve dramatically out of the way. Is that up? Okay. Now, yesterday we talked about something called plus-minus notation. It says list your breakpoints, then mark them on a number line. Make the number line big enough to capture all of these. So,
It, I'm just gonna tell Julia, the word, right here at the sideways says discontinuity. She can't see that, but she can see everything else.
oh, whoops.
You shouldn't move it because
Okay,
she
okay,
can
good
see
catch.
it direct, so.
Good
The word
catch.
that's
Thank you.
slanted says discontinuity.
Discontinuities, that means an interruption. Yeah, thank you. What is the smallest, furthest to the left breakpoint? Which I start with?
-5.
-5. So I'll mark this as -5. You don't have to be, artistically perfect as far as spacing these. The next one is -2, I think. And then there's one at -1. There's one at 3. And then one at 5. So you remember these. How do you mark a root, Jack Law?
With a dot,
What kind of dot?
the close.
Closed dot, correct. Roots are with a closed dot, solid dot. That's focus here. I doubt that the whispering is germane to the topic. So solid dot at -2, solid dot at 3. I forgot 4. What the heck? I shouldn't have been a +5. Does that make sense so far? How do you mark vertical asymptotes, Michael?
The dot line,
Yeah, what direction?
vertical.
Vertical, a teeny weeny vertical dotted line. So at x equals -1, you don't even have to go all the way through, just as long as I can see it, and then -5. Does that make sense so far? This is like a miniature of the graph. What they suggest after that is look and see how many regions this line has been broken into. So there is a region, in each breakpoint, it's going to break it here, 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 and here. How many regions does that make total?
6.
6. I'm going to call them region A, B, C, D, E, F. Now, part of the secret is, the reason I marked all of these is because the graph is probably going to change sign from positive to negative. If it does, it's got to do it at a breakpoint. What does it mean when a graph changes from positive to negative? It means it's soaring above and then it plunges below the x-axis. That's what it means. If it's above or it's below, this will tell us ahead of time where the graph is, above or below. Okay. When you try to graph this, even on a graphing calculator, if you got one, these get really complicated really fast. Especially if I have high powers, like to the 7th power or something like that. I have, in my previous job, everybody had graphing calculators and iPads and blah, blah, blahs. And they were very reliant on the calculators. So I said, okay. I cranked these up to 8th power, 4th power, whatever, really high power. And I said, okay, type it into your calculator and graph. First of all, a lot of them forgot that you have to have parentheses around the bottom and around the top. Otherwise, the graph will be wrong. So a lot of people fell at that challenge.
Is that how graphing calculators work?
Mm-hmm.
You can just type that in and it'll give you the answer?
It's annoying to type in, and then it should give you the graph, but there's a disadvantage. The normal graph is from negative 10 to 10, like just the plain old graph if you don't mess with it. It goes from x is negative 10 to 10, y equals negative, a normal graph. Usually the graph of this is much, much bigger. So a lot of it's off screen. In addition, the powers are so high, normally you're expecting something that looks like this, or you might have something that looks like, swooping this, and then, maybe like that. Something recognizable. Here's what they actually got. And that's all they saw. And then they started panicking. They said, well, is this going up or going down? It went by so fast, you just can't tell. If I crank these powers up really high, this thing will torpedo so fast that you can't tell if it's going uphill or downhill. It looks like a vertical line. If you shrink it, it might look like this. If you crush it down, it's like going way, way, way high up and then way, way far down. But there's no way to know that. That's why plus-minus notation is great. It doesn't matter if your calculator fries itself graphing or not. We'll know if the graph is above or below. And we also know that it will never change unless it hits a breakpoint. If it doesn't hit a breakpoint, there's no way it's going to change from positive to negative, ever. So, how do we tell, like in region A, if it's positive or negative? Yeah.
We choose a number in that region and then plug it in.
Yeah, test a point in there. It's kind of like, remember when you were shading? You pick a point and test it. Same sort of thing here. Can somebody pick a convenient, easy number in region A? Go ahead.
-6.
-6 sounds good. I would not choose -5 because that's on the boundary. So x equals -6. I'm about to show you a bit of a shortcut. I don't really care what the answer is when if I plug in -6, this is going to be kind of gross. And it's also going to be a huge number on top, huge number on the bottom. I don't care what the number is. I just want to know if it's positive or negative. Does that kind of make sense? This will be, I might have like -3 billion over positive 2,000. I don't care about the numbers. I just want to know, is it negative over positive? Oh, then it must be negative. Does that make sense? So, I don't care about the numbers. Watch this. Up here, I'm going to do this. See what I'm about to do? I'm going to recopy this, a little squared here, a little cube here. But all I'm going to put is either a plus or minus. You tell me. If I plug in a -6, what's -6 plus 2? Yeah. -4, so it's just negative. Plug in a -6 here, positive or negative? Negative, it would be like -9. -6 in here? Negative to the 3rd power. What about -6 here? Negative. How about -6 here? How many negatives total? Now remember, there are 2 here.
8.
1, 2, 3, 4, 5, 6, 7, 8. What happens if you have 8 negatives all multiplied together?
Positive?
That's positive. Congratulations, you just nailed down zone A. See how that works? I didn't even care what the numbers are. I just know this zone, this region, is positive. That means the graph is above the x-axis there. Choice B. Somebody pick a nice number to test. Jenna, help me out. What's a decent number to test? -3, sounds good. So let's try x equals -3. And I'm going to try this same thingy again. This will be squared, cubed. Plug in a -3 for that upper left. Negative. It'll be a -1. -3 in the middle.
Zero, so.
Uh,
Oh, sorry. No, still negative. Sorry.
Still negative, -6. -6 in that one.
Negative.
Negative. How about here?
Negative.
How about this one?
Pause.
This one's positive. -3 plus 5 would make 2. Simplify this. How many negatives total? There are 3 here. 7, because this is positive. What is 7 negatives times a positive going to give you? That's negative. Because any odd number of negatives is going to give you a negative. This zone is negative. Anybody see a pattern going on here? Yeah.
So I can answer that. It's alternating, but also if you do get a 0, would it be positive when you're going through?
Oh, if you hit a like if you actually get a 0 in here? Okay. If you actually get a 0, that'll actually be one of the roots that we wouldn't be testing.
Okay, yeah.
So yeah, that's a good question. So if we got an answer of 0, that means it would have been in our list of roots in the first place. And we're trying to get in between the breakpoints. So hopefully it should be safe. Try the next zone, somebody. Give me a number in between here and here. Go. -1 is actually on the bottom.
Oh, sorry. -1/2.
Close.
I mean, 1.5.
Yeah, I'm actually going to do a decimal. Boy, mark this on your calendar. X equals -1.5. It should still be relatively easy. All I care about is positive or negative. So the 3 parentheses, squared, cubed, paren. Okay. So what about here? -1.5.
Oh, me?
Yeah.
Oh, sorry. It'd be positive.
That's positive. How about here?
Negative.
Negative. How about the next one?
Negative.
Okay.
Positive.
Negative barely.
Okay. Positive.
Positive. How many negatives total?
3.
There's 3 here.
Sorry. 5.
5. There are 5 negatives. What does that mean?
This negative.
Anybody surprised by that? What were you expecting?
Positive.
We were expecting it to go positive, negative, positive, negative, positive, negative, positive, negative, positive, negative. What's going on here? You see the -2 there? What kind of a root was it?
Negative.
True.
Times
It's a double root.
Oh.
And over here is a triple root. Why did it not switch sign? Well, the answer is it did switch sign. Watch this. If I switch this light switch, did things change? Yeah, it went from light to dark. Now watch this. I want to make sure I don't break it. Now I can't do it instantly, so I don't want to snap the thing, but watch. Is here. I'm going to change the switch once. Is the end result different? Yeah,
Yeah.
it's darker. Watch this. Is the end result different?
No.
No. If you switch it twice in a row, you'll get back to where you started. What it did was positive, negative, positive, negative. It switched twice. Guess what'll happen here?
It would just be the same.
It'll switch 3 times in a row. Make sense?
Which will make it different.
You have just found a much, much faster way to get all of these. I was going to tell you this in about 10 minutes. You're faster than I am. You can count on the fact that it'll always alternate every switch. But just remember, sometimes it switches twice. Sometimes it switches 3 times or 4 times or 5 times.
So it'll alternate unless it has a higher degree.
Correct, and then it'll alternate a whole bunch of times in a row. And then you can sort of do it in your head. Like if it's a quadruple root, it'll be on, off, and it won't change.
So this one, so it's positive, negative, negative, and the next one positive.
Yeah,
And
because you
then-
notice in -1, it's a regular single. That switches. Single roots and single asymptotes will always switch. Yeah, Sophie.
So, basically all the only one we have to find is like the first one.
Yes.
We can just go from there.
And the funny thing is, you don't even have to start there.
You can see.
People who are totally sneaky, they start in this region and plug in 0 just because it's so easy. And they can work forward and backward. Isn't that totally sneaky? If you know it's going to alternate, you can start anywhere. And then just go plus minus, and then just make sure that some of these flip twice or 3 times. Single root, is that going to flip or no? Yeah. What about a triple root? Is that going to flip? Think about that for a second.
No.
Yeah.
Oh, yes, sorry.
Yeah, double root wouldn't,
Um,
but a triple root will flip it back. So it'll go plus minus plus. Oh. So it actually did ultimately flip. Every pair of flips cancel out. Kind of like 2 negatives cancel out. It's kind of like this. I'm going to flip this switch 3 times. Tell me if the end result is different.
It is.
Yes, it is. Now, I'm going to flip it 4 times in a row. Is the end result different?
No.
No. See how that works? Yeah.
So, is it the, you said you looked at 3 for section E, or you looked at 3 and you said that's a.
Oh, this is a single root.
Yeah, okay, it's a single root.
Uh-huh.
So, does that mean that?
That's kind of like the equivalent of flicking the light switch once.
Yeah, I understand
Uh-huh.
that, I just, but I don't know how I'm gonna ask this. So, 3 is a single root, so does that mean section E is like based on number 3? Because we know it's a single root?
Yes.
Even though it's between
In other
3
words,
and
if I
4?
knew this is positive, and I just crossed a single switch, it'll switch.
Okay,
Now, if this were a double root, it would go minus plus, and the
Okay.
end result would be positive again.
okay,
So it's pretty much saying each of these things, each of these breakpoints is like switching the light switch once.
got it.
A double root is switching it twice, which kind of cancels itself out. Triple root is like a normal switch with a bunch of extra exercise.
Okay,
Is that right?
yeah. thank you.
And you notice we don't have to plug in any more numbers? You could. If you tested a number between here, I guarantee you'd get a positive answer. In here, I guarantee you, like 3.5, final answer is negative. Over here, if you plugged in x equals 10, it's going to be positive. That is plus minus notation. Now, let's see if we can actually draw a sketch of this graph. A real honest-to-goodness sketch will involve a few things. First, oh yeah, I have one more kind of surprising thing to tell you, but one thing at a time. The sketch should be the following. Let me see. You should have what we call end of behavior. I mean, start up, start down, end up, end down. Second, you should have all the roots, which are basically the x-intercepts. You should have the y-intercept. You should have any vertical asymptotes. You should have any holes. And I want the exact location. There aren't any in this problem. I'll give you one in the next problem. Let me see, what else? Oh yes, and you should do above / below. And you should also do the through versus bounce versus swerve. let's see if we can put this all together. Again, the graph doesn't have to be perfect, but we can get more accurate than you expect. Can anybody tell me where the roots are, first of all? Those I can actually graph. Michael, where are the roots?
You want me to just name them? Like,
Yes, please. There should be -2. Okay. What's another name for root? X-intercept. That's why I wanted them, because they're actually going to be on the graph. So -2, and what kind of a root is that, by the way? Double root. Okay? Keep going.
3,
X equals 3. What kind of a root? Single. And then 4, and what? That's a triple root.
-1 is, oh,
Yeah, go ahead.
vertical asymptote, so
Vertical asymptote at -1. Draw the full-fledged dotted line up and down at -1. Single, double, or triple?
single,
Single. Put a little times 1 at the bottom. Any other vertical asymptotes?
-5,
At -5.
is single,
3, -4, -5. Single, so make the nice big huge one -1. Okay? Now, end behavior is, does it start from above or start from below? Normally it's very, very hard to tell. If you know the basic shapes like cubic, positive, negative, blah, 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 you can do that. We have a key to the whole thing. We have the plus minus notation. We now know that it has to start from above. And it has to end what?
you follow,
What?
that point starts.
Oh, low power mode, fine. I hope that kept recording. Hi, Julia, just in case it didn't.
It didn't. You're at 31 minutes.
Okay, we're good. I put it on low power mode, so it should be good. Yeah, Sophie.
So what would a double vertical asymptote look like?
Double vertical asymptote, you do a dotted line and put a ×2 here.
But,
What does it do to the graph?
yeah,
Okay, the other day we covered a double asymptote. Like an asymptote, you know the graph swerves. A single asymptote, they swerve opposite ways. Double asymptote, they swerve the same way. Then triple is opposite, quadruple is same. Now, they could go down, I suppose. There's nothing stopping it. If it's a negative graph, they might both go down for double asymptote. So, single asymptote. We're starting from above. Here's a quick question. Do I start above the x-axis or below? To start from the beginning. Go. Above. I have to swerve to avoid this asymptote. All math people. Yeah.
Mr. Carpenter,
So-
let's scooch this over a little bit.
Go ahead.
It's kind of cutting off the graph a little bit.
Okay. Okay, thank you. Should I swerve down or up? Detectives.
Down.
There's a problem with going down though. Guess what did it cause?
an x-intercept?
It would cause an x-intercept, also known as a root. And we don't have a root there. These are the only roots that'll ever be in here. So what has to happen?
Has to go up.
Has to go up. It's going to go up forever. Now, here, is it going up forever? I honestly don't know. Could it be flattening out? Could it be going up? I don't know. And I don't care. I just want to know it's on the upper side. Question. Where do I reappear on the other side of the asymptote?
Sorry, I have a question. I don't understand, why did you just start it randomly in the middle?
Oh, because I have no idea how high it was when it started. All I know is it couldn't have been below. It could have started way up here, could have started way down
So
here.
that just doesn't pertain to us at all?
Correct. Not yet.
Just
That'll
like
be-
that
that'll be
whole
next week.
line, we just don't even,
Yeah, right now, it's sort of like, I just want to know, did I start the above or start from below?
okay.
And right now, we start from above. Like, where did it actually come from? We'll cover that later. It's not in this assignment. What about in the next zone? This is -5, by the way. And this is -1. So between -5 and -2, is the graph above or below? Look at the plus minus notation, it should tell you.
It's below.
It's below. It comes from here. Now, do you think I can swoop down from here and go below?
No.
No. First of all, it would be above for a while, and it would give me another root that I don't want. it has to come from way down here. See why? That's the only place it could have come.
Why do we?
The asymptote means it has to swerve and get closer and closer and closer, but it couldn't have swerved from above because there's nowhere in there that's positive, because if you're up here it's positive, and it would have given us an extra root that we don't want.
If
So it
comes
had to come from below.
If it comes from the bottom, why is it going down?
Oh, okay, depending on if you're reading from left to right. If you're reading from left to right, it's coming up.
Okay.
I'm just saying, it is swerving to avoid this
Are
asymptote.
you done with that line?
With this line right here?
No, the one that you're drawing with the arrow.
Oh, no, I'm gonna keep going, but I don't know where
I
it's
thought you
going
were
yet.
just pointing down, because I thought it was done like the other.
Oh, no, sorry. I'll put a question mark if it were. Now, it looks like we're about to hit a root. Tell me what happens at that root, Polly. What kind of a root is it, first of all?
It's a double root.
Is that go through, bounce, or swerve?
It's a bound.
That's a bounce. So what happens when it bounces? Where does it go?
Goes back down.
And does that agree with our, yes it does. That's nice when it agrees. And it's about to hit another asymptote, so it's going to swerve away from that. You see what? Every time you get near an asymptote, it's going to get closer and closer and closer, but it's never going to touch. It'll go forever and never touch. Now I've got a new zone from -1 to 3. What should the graph be there, P? Is this zone, is the graph above or below?
Would it be
Above, because it's positive. Now over here, here's the asymptote it was trying to avoid, and I gotta be above. It's doing this. Does everybody see that you're gonna get a y-intercept in there somewhere? I have no idea where it is, but do you see where if I'm gonna swerve and hit this root, I gotta hit the y-axis? So I'm swerving for remove the asymptote, but eventually I have to cross over here. So you tell me, when I get to 3, Julie Miller, what kind of a root is this?
It's a
Single root. What's it gonna do?
It just goes straight through.
Go straight through. So it's going to, boom. Does that make sense? I don't know exactly what angle it does, but it's going through. It doesn't bounce, it doesn't swerve. What's gonna happen after that? Noah?
This can go down
Down for a little bit.
and then come back through and swerve through 4
Uh-huh. And then do what?
and then go up.
And go up. And I don't know how far. It might flatten out, it might go forever. I don't really care. But you see that there was a swerve there? A triple root always swerves. It flattens out and then keeps going up. That agrees with this. The positive, which is above, then for a teeny weeny little time it's below, and then it goes above again. That is a decent sketch of your graph. I just want one thing, and I haven't shown you how to do this yet, but it's kind of slick. We haven't found the y-intercept yet. Tell me how. It's actually not too hard. Yeah.
Just where the graph crosses the line.
Right.
On the y-axis.
Right. How would you find that? Because I didn't graph that very accurately, so I can't just measure.
The slope?
No, but a little hint. Think chubby hand method. Y-intercepts always look the same. They all have something in common. Yeah.
Oh, this is a different question. I'll wait a second.
Okay. How do you get a y-intercept? Oh, math people.
X equal to 0.
If x equals 0. Here's the original equation. Plug in x equals 0. Here's what you get. Y equals, this time I want a number. Plug in a 0, what do you get? 2 parentheses squared. How about here? -3, keep going. -4 cubed. All over what? 1 times 5. Calculate. 2 squared is 4 times -3 times, let me know, -4 cubed. -4 times -4 times -4. Is that going to be positive or negative? Negative something. Anybody know?
56?
You're on the right track.
60.
Negative 60.
2.
What's 16 times 4?
4. Negative
64. Right. All over 5. So now this, you see it's going to be positive? Negative times negative?
Wait, wouldn't it be 6?
Well, 4 times 4 is 16, times 4
Oh,
is
sorry, times,
64.
sorry.
Huh? Now, these make positive. I'm going to do 64 times 12, because that's 12. I have no idea what that is. Let me do it over here. So it's 12, 64, 8, 6, 768. So it's going to be 768 over 5. That's your y-intercept. You never would have known that. By the way, 768 over 5 is big. This is 100, that's 2 left over. 153 3/5. That's huge. But that's the y-intercept. Yeah, Sophie.
So all we have to do is label it.
Correct. Yeah, you do not have to do dashes. That would be obnoxious. Yeah, make sense? So you already got the x-intercepts by the breakpoints anyway. Now you got the y-intercept. That's pretty much the last thing you needed to do. There are no holes in this one. You got the above and below from the plus-minus notation. You got the through, bounce, and swerve. We're done. Question?
So do you need that before the first vertical asymptote? Do you need that arrow going up?
You do need the arrow going up, yes. We do know that that's going to go up forever because it's got to swerve to avoid the asymptote.
Can we put an arrow where you have the other question mark on the other end?
Well, the problem.
Not there, on the other end.
On here?
Yeah.
I don't know. Part of it, could it do this? Yes. Could it do this and flatten out? Yeah. Could it do this and go back down and just barely skim the x-axis? Yeah. I have no idea what it's going to do.
So you want us to put question marks on the end?
Yeah, for now. A little later on, I'll show you how to find the actual end behavior, like the infinity and negative infinity. We haven't covered that yet. That's a new lesson. Questions? Right, let me grab the thing that just came off the photocopier. Got one. If it isn't, I'll yell at it.
Hey, Julia.
Hey, hey. There's a lot of quarantine, so if you could, that'd be great. But I hope you're feeling okay. Maybe like AC
Yes,
back.
indeed.
Okay, bye.
By the way,
10% left.
okay, thank you. I think we're done. So,
Hi, Julia.
see you later.